Okay. So now we have this sequence, that is sequence of actions. Okay. Now if we couldn't find any possible sequence from the current state to the goal state, then the search will return failure or null in the sequence, and then we don't have any set of actions, so the action will be returned null. There is no possible action from the current state to reach to the goal state. Now if this is not the case, then there will be no return, and from sequence we will directly come over here. Now we have a complete sequence of actions in this sequence struct. Now when in a loop, every time we get this percept, we will see that we will see if this is the first time we receive a percept from environment, then we will see if the sequence is not empty. We need to formulate goal, problem, and search for a desired sequence to reach to the goal state. But if this is not the first time, then we have a sequence that will take us to that will take to the agent to the goal state. So if this is the first time, this will be set, and from that sequence we will extract first action and will return this action for execution, and the rest of the sequence, once the first action is extracted, the rest of the sequence will be kept in this sequence struct. Okay, every time this method will trigger, it will give us an action from that sequence until the sequence is completely empty. So if the sequence is completely empty, it means all the actions are executed, and now the problem is completed and we reach to the goal state. So this is a generic method for finding, a solution to the problem of Romania Turing problem. Okay. Now what could be the aspects we need to consider while dealing with a simple problem solver or problem solving agent? We need to assume that the environment that the problem solving agent is dealing with should be a static environment, and we know from previous lectures that what exactly static environment mean. And also the environment should be observable, it should be discrete, it should be deterministic. Okay, and then a new term, that is open loop. So let's see what open loop is, because we have seen this for the first time. Now we use this term open loop for problem solving agent because once after the first percept, once we receive a clear picture of the problem and our goal state, so we can calculate, we have seen this in the previous algorithm, we can calculate the desirable sequence to reach from the existing state to the goal state. So once we receive that sequence, there is no need to uh, consider other percepts. So in that case, we don't consider, we don't take the receiving percepts into consideration, because now we have all the possible actions, all the actions required to reach to the goal state. So we just uh, closed our eyes, or you can say the agent closed his eyes or her eyes, and it just take the actions that are predefined in the sequence that is calculated based on the goal and problem. So this particular setup is what is called open loop, because now you don't need to consider the percepts you're receiving from the environment. So because of this open loop, the break between, the connection between agent and environment uh, becomes, I mean, less useful, because we don't need now percepts for the environment. We know our environment, we know, and the environment is discrete. Yes, we have said this, these aspects. The environment is discrete, deterministic, is observable, it is static. So if all these features hold, then it does make sense that if you have all the possible actions that will take you from the initial state to the goal state, and there is no need to consider percepts from the environment, because environment is not changing, it is static. So you can quickly perform or execute the actions that sequence gives us, and the agent will reach to the goal state without any hurdle. So this particular scenario is called open loop. Okay, now under these assumptions, we have said the solution to any problem is a fixed sequence of actions. So if we say the environment is static, it is observable, it is discrete, it is deterministic, so then we can say that now the solution is just a fixed possible actions, a sequence of action. Okay, now we actually saw a method of problem formulation in the previous slides, but we didn't go into the details of that problem formulation method or function. Now we will see that what are exactly inside the problem formulation method, and what are the steps required and executed in this particular method. Okay, now while formulating a problem, first you need to decide initial state, and this initial state is basically the state in which you are standing currently or presently. So first thing, you need to decide the initial state. The other one is action, all the possible actions. That for this particular problem, what sort of actions are required, or what are the possible actions. So the first set is initial state. The second one is uh, all the possible actions. The third one is transition model. And what does this transition model mean? That you need to have a function, the agent must have a function that takes the agent from one state to another state. Okay, so now the method for this particular set is result. Now this result method takes the current state and possible action, one of the possible actions, and take the agent from current state to another state. So this transition is what is uh, the output of the transition model. So we have seen three sets. The first one is initial state, the other one is all possible actions, then transition model, and then the other set is goal test. So every time we arrive on a state, we perform a goal test. That is, whether this state is our goal state or not. So the output of the goal test is going to be a binary. That is, it could be yes, it could be no. So if the state we are arrived in is a goal state, the goal test will give us yes, or yes, this is the goal state. If we arrived in a state and that is not a goal state, so the goal test will give us false, no. And then the last the last parameter of the problem formulation is path cost. So each action has a certain cost. Okay, so let's say if we take this action, so the cost of this action should be added to all the actions we have performed previously, and this will become path cost from the initial state to this current state. Okay, so in problem formulation we need to decide initial state, we need to decide possible actions, we need to decide a transition model, we need to decide a goal test, and we need to decide a variable, or you can say a container, that will keep the path cost. Okay, now we take this Romania Turing example and formulate its problem. Now the initial state. Now we know that the agent is now standing in the arid city. So the initial state is the arid city. Now from this arid city we can see in this agent is sitting here now. From arid city, the agent can go to CPU. The agent can travel to Timisoara. Okay, this is another city. So the from arid, the agent can go to Timisoara, and the agent can go from arid to Zerid. So we have three actions. Whether go to three possible actions from this state. Whether we could go to we can go to this Zerid, we can go to this Sibiu, and we can go to this Timisoara. So these are the possible actions from current state. Okay, what could be the transition model for this state? Now the model is, if you are in arid and you decide go to CPU, so from this if we go this action in arid, this is the current state, and this action go to CPU. If we give both the state and that possible action to the result method, it will give you the next state, and that is if you are sitting or you are standing in array and you decide to go to CPU, so you will arrive in CPU. Now the next state is in CPU. So this is the possible transition model for this problem. Now we know that our goal is to reach to the Bucharest. Now the goal test is whether the agent is in Bucharest or not. So this is goal test. So this is your goal state. I mean the Bucharest, in Bucharest your goal state, and the goal test is to see if the current state is Bucharest or not. Okay, now we have set all the parameters, that is initial state, actions, transition model, goal test, and now the last one is to calculate path cost. So the path cost is basically the distant travel, and that is basically the additions, the sum of step cost. So if you are in the agent is in X state and it performs action A, it reaches to state Y. So if we give both these states and the action to the method C, so C is responsible for calculating path cost. So this will give us step cost, and all these when we add all these step costs, we can calculate the path cost. Now, what could be the possible solution to this problem? We have seen, now this is our problem. We have formulated a problem which is given in the form of this, you can see this map. Now this is our problem, and this is understandable for the agent. Now the solution is a path from the initial state to the goal state. We need to find path from initial state to goal state. This is our solution. So solution, there may be many solutions for this problem. There may be many routes to be followed to reach to the goal state, but the optimal solution is the path that is the lowest path cost among all solutions made by the path cost function. So that particular solution which has the lowest path cost will be considered as optimal solution for this problem. Okay, now there are challenges and there are problems while formulating a problem. So what are these challenges? Real world is complex and has more details. We have seen that all the previous formulation was based on the assumption that the word should be observable, it should be discrete, it should be static. Now in reality the world is very complex. It doesn't have like these assumptions. There are other factors we need to consider while formulating a problem. Compare the simple state description we have chosen in array. Now we choose that we are in array, and that was just a state. Now there are certain assumptions we had made at that level, but we didn't consider other information and other aspects. Those are to an actual cross-country trip where the state of the word includes so many things. That is, the traveling companions, what are the companions you are traveling with, the current radio program, that is tuned on your radio. The scenery out of the window. Okay, the proximity of enforcement officers. So how close the law enforcement officers are uh, to your car, or whatever source of travel is. The distance to the next rest stop. So these all these aspects and all these things will actually affect your decision of taking such a certain action while you are in the current state. The condition of the road and the weather and so on. So these are possible. I mean, some of the possible uh, aspects that we normally ignore while formulating problem, because it actually increases the complexity of the problem. So we ignore these things and we just say that we are in error, and now we want to go to the bokeh register, CPU, etc. So we don't consider that which road is I mean, in good condition, and the, which road has more than one stop, etc. So we don't consider these things in order to simplify the problem. Now, all these considerations are left out of our state description because they are irrelevant to the problem of finding a route to Bucharest. So now the goal is to reach to Bucharest, and that should be dominant. So that's why while dealing with certain, I mean, such problems, we exclude irrelevant complications and aspects. The process of removing detail from a representation is called abstraction. So in the real world, yes, these things exist. These things are considered while taking decisions and actions. But while formulating a problem for an agent, we normally exclude these detail. So excluding these detail and removing these detail, the process of this removal is called abstraction. So once we get a problem from real world, we perform abstraction to make it simple for the agent. What's the appropriate level of abstraction? So now we need to decide a level of abstraction, that how many things to be removed and how many things to be included. So now the appropriate abstraction level should be the level that should kept the abstraction valid. That is, if we can expand it into a solution in the more detailed word. So now your solutions should remain valid. So that abstraction level can be considered appropriate, that could maintain validity of the solution. I mean, for example, let me give you an example. If you want to remove irrelevant details in order to simplify the function, the problem, so you need not to exclude those details which are important and relevant to the problem. If you exclude those aspects and those complications or considerations, then your abstraction will become invalid. So you need to remove irrelevant details, but keeping an eye on the validity of the problem. And the other one is the abstraction should be useful. So the abstraction should be valid as well as useful. What does this usefulness mean? If carrying out the actions in the solution is easier than the original problem, the abstraction should be useful. This means that the problem that you have now the abstract problem that you have designed should be easy than the real problem and the actual problem. If this is not easy, then this is more complex than the real problem, and this abstraction is not useful. We don't need this type of abstraction. So, to decide the appropriate level of abstraction, you need to consider the validity and usefulness of the abstraction. So you need to remove as much details as possible while retaining validity and usefulness of the problem.